the Southern Ocean. It's this vast, wild place,
Yeah.
you know, and it's way more than just icebergs and wildlife. It's actually critical for our planet's climate.
Absolutely crucial. But for years, there's been this nagging problem with climate models trying to simulate it.
A gap, right, between the model predictions and what we actually see happening down there.
Exactly. A persistent gap. And what's really exciting is we might be getting closer to understanding why.
Okay, so let's get into this mystery then.
We're going to explore a source of marine sulfur emissions that hasn't gotten much attention until now. And it seems to play a much bigger role in cooling than we realized.
Right, so for this deep dive, we're digging into a fascinating new study. It's just been published in Science Advances.
And it really shines a light on this sulfur gas that, well, it's kind of been hiding in plain sight, climate-wise.
To really unpack this, we'll be focusing mainly on that Science Advances paper. The title is Marine Emissions of Methanethiol Increase Aerosol Cooling in the Southern Ocean.
And there's also a helpful press release from the University of East Anglia, UEA, that explains it nicely, too.
So your mission today, if you choose to accept it, is to understand how this newly measured sulfur gas, it's called methanethiol, or MET-SH for short, how it's changing our view of ocean-driven climate cooling.
Yeah, it really looks like this could help make climate models much more accurate, especially for that tricky Southern Ocean region.
Definitely some aha moments coming up, especially considering this gas was apparently notoriously hard to measure.
And the impact. Surprisingly big.
Okay, so before we get to MET-H, let's quickly recap the traditional view. For decades, it was all about DMS, right? Dimethyl sulfide.
Pretty much, yeah. DMS was seen as the key player, the main marine sulfur gas contributing to cooling.
How does that work again?
Well, the idea is marine life produces DMS, it gets into the atmosphere, reacts, and forms tiny particles, aerosols.
And those aerosols reflect sunlight back out.
Exactly. Both directly reflecting sunlight and also by making clouds brighter, which also reflects heat. This understanding was central to the see-all hypothesis.
Ah, yes, the idea that marine life could sort of regulate the climate through DMS.
That's the one. So naturally, climate models have focused heavily on DMS for a long, long time.
Makes sense. So enter MET-H. What is it and where does it fit in?
Okay, so MET-H, methanethiol, is another sulfur compound. It's also volatile, meaning it escapes into the air easily, and it's produced by marine life, too.
Alongside DMS.
Yeah, it comes from the breakdown of the same precursor compound, actually, a molecule called DMSP, dimethylsulfoniopropanate. Phytoplankton make loads of DMSP.
So DMSP breaks down into both DMS and MET-H.
Correct. But while we knew MET-H was produced, its actual emissions, how much gets into the air globally, and its climate effects, that was largely, as the paper says, unexplored.
Why was it so unexplored if it comes from the same source?
The big problem was measurement. MET-H is just really, really reactive chemically.
Ah, so it disappears quickly, making it hard to track.
Precisely. It's difficult to get accurate concentrations in seawater, let alone in the air. Plus, a lot of the earlier research may be focused more on warmer waters.
And this study suggests that was missing something important.
It seems so. They point to the polar regions, especially the Southern Ocean, as being MET-SH emission hotspots. We might have been looking in the wrong places, or, well, not all the right places.
Okay, so measuring it is tough.
Yeah.
How did this team manage to quantify the emissions then? What was the breakthrough?
Well, they did something quite impressive. They compiled a huge database of MET-SH measurements from seawater.
Not just old data.
Now, importantly, they included brand new measurements from several research cruises. Crucially, one called Polar Change that went to the Southern Ocean.
Okay.
And also year-round data from an observatory in the Mediterranean, Blaines Bay. So a real effort to get new, relevant data.
Wow. That sounds like a massive amount of data collection.
Yeah.
What kind of range did it cover? Geographically, temperature-wise?
It was really comprehensive. Covered latitudes from the Arctic all the way down to the Antarctic, a huge range of sea surface temperatures, different levels of biological activity, indicated by chlorophyll A.
Chlorophyll A. That
Yeah.
tells you how much phytoplankton is around.
Exactly, the base of the food web. So yeah, a very broad data set, giving them a much better foundation to build on.
So they have all these point measurements.
Yeah.
How do you go from that to a global emission estimate? That seems like a big jump.
They developed a pretty smart empirical model. Basically, it uses two key factors: sea surface temperature and whether the water is over a shallow continental shelf or out in the deep open ocean, the bathymetry.
Okay.
And using those factors, along with the known DMS concentrations, the model predicts the likely MET-SH concentration. It sort of links MET-SH to DMS, but acknowledges the relationship changes depending on the environment.
Ah, so it's not just a simple fixed ratio between MESH and DMS everywhere.
No, definitely not. That's a key finding. They found MESH emissions are, yes, linearly correlated with DMS, but the ratio changes. In cold open ocean waters, like the Southern Ocean, you get a higher proportion of MESH relative to DMS. But on shallower continental shelves or in warmer open waters, the MESH proportion is lower.
Interesting. Suggests different biological or chemical processes are dominant in different places.
Precisely. Environmental factors clearly play a big role in modulating that MESH to DMS production pathway.
So the big numbers, what did they estimate for the total global MESH emissions? How does it stack up against DMS?
Okay, the global annual estimate for MESH emissions came out at 5.7 teragrams of sulfur per year, plus or minus about mid 0.6.
And DMS, what's the current number for that?
The best estimate for DMS is around 23.5 teragrams of sulfur per year.
Okay, so MESH is smaller overall, but still significant. What's that as a percentage?
Globally, MESH accounts for about 19% of the total biogenic sulfur coming out of the oceans, almost a fifth.
Wow, okay.
But here's the kicker. In the Southern Ocean, that proportion is even higher. It's around 27% of the total marine sulfur emissions down there.
So nearly a third of the sulfur gas in that critical region is actually MESH.
Looks like it, yeah. And similar to DMS, these MESH emissions peak in the high latitudes during their summer when the phytoplankton are most active.
Okay, so a significant amount of MESH is getting into the atmosphere, especially down south.
Yeah,
How does that actually affect the climate then? This is where the atmospheric chemistry kicks in, I guess.
absolutely.
Yeah.
This is the next crucial step. The researchers took these new MESH emission figures and plugged them into a sophisticated global climate model. It's called KMChem.
A model that simulates atmospheric chemistry.
Exactly. It simulates how different gases interact and transform in the atmosphere, and the results were, well, quite striking.
What did they find?
Adding MESH emissions dramatically increased the total amount of volatile methylated sulfur, that's basically DMS plus MEH in the atmosphere. Globally, the increase was 34%.
34%. Just from adding MEH.
Yep. And get this.
Right.
In the Southern Ocean, the increase was even bigger. 51%.
Whoa. So MEH has this huge amplifying effect on the total available sulfur, particularly there.
Massive effect. But here's where it gets really interesting and maybe a bit counterintuitive.
Okay.
The model showed that including MESH didn't just add its own sulfur, it actually increased the amount of DMS in the atmosphere too.
Wait, what? How? The DMS emissions from the ocean were the same in the model, weren't they?
They were kept constant, yes. The emissions from the ocean didn't change for DMS, but the amount in the air went up by 11% globally and 17% in the Southern Ocean.
That doesn't make sense on the surface. Adding one gas makes more of another one appear.
It's all down to the chemistry. MESH is much more reactive than DMS. It reacts faster with the atmosphere's natural cleaners, oxidants like OH radicals, bromine monoxide, things like that.
Okay, so MESH is like hogging all the cleaners.
That's a great way to put it. Because MESH reacts so quickly, it uses up these oxidants. That means there are fewer oxidants left available to break down the DMS.
So DMS sticks around for longer.
Exactly. Its atmospheric lifetime increases. The study estimated that MESH extends the local lifetime of DMS by about 1.2 days in the lower atmosphere over the Southern Ocean.
So it can travel further, build up more.
Precisely. So even though the ocean emits the same amount, more DMS persists in the air because MESH is essentially running interference, taking the hit from the oxidants. It's like a chemical bodyguard for DMS.
That's fascinating, a bodyguard gas.
It is, and there's more. The breakdown of MESH itself also produces sulfur dioxide, SO2.
Which is also important for aerosols.
Very important. The model showed that including MESH emissions basically doubled the amount of SO2 near the sea surface, around 65 degrees south.
Okay, double the SO2. So connecting the dots. More SO2 means more aerosols, right? And that's where the cooling comes in.
You got it. The increased SO2 leads directly to more sulfate aerosol formation, and this effect was really concentrated over the Southern Ocean, a 70% increase in sulfate aerosols in the lower troposphere down there.
70%, that's huge.
It is. And these extra aerosols cool the climate, primarily through reflecting sunlight directly. That's the direct radiative effect, or DRE.
And how much extra cooling did they calculate from this MESH effect?
They found an average annual increase in this direct cooling of 28% between 40 south and 70 south latitude.
28% more cooling just from adding MESH.
And it peaked at around 50% more cooling near 65 degrees south during the summer months. That's a cooling effect of about 0.00075 watts per square meter in January there.
Wow, and this is where it ties back to that original puzzle, isn't it? The climate models being too warm over the Southern Ocean.
Exactly. This is the crucial link. For years, models have had this positive radiative bias over the Southern Ocean summer. They let too much solar radiation reach the surface compared to observations.
By how much?
It varies, but somewhere in the range of +4 to +15 watts per square meter, too much radiation. It's been a real headache.
And the location and timing of this bias.
Lines up remarkably well with where and when this study finds the peak MESH-derived aerosol cooling effect.
So the implication is that adding MESH to the models could directly counteract that warm bias.
It strongly suggests that, yes. By adding these MESH-derived aerosols, the model should simulate brighter, more reflective clouds, reducing the amount of sunlight reaching the surface, and potentially closing a significant part of that long-standing model observation gap.
This feels like potentially a really big piece of that Southern Ocean puzzle finally clicking into place.
It really does, and that's just the direct effect. They also looked at the indirect effect.
That's how the aerosols affect the clouds themselves, making them brighter or last longer.
Exactly. The indirect radiative effect, or IRE, their estimate suggests this could also be significant, potentially adding another -0.3 to MESIS of 1.5 watts per square meter of cooling in the Southern Ocean summer.
So the total cooling impact could be even larger?
Potentially, yes. There's more uncertainty in estimating the indirect effect, but it certainly points towards MESH having a really substantial role in the region's energy balance.
This is clearly about more than just aerosols, then. Altering the atmospheric chemistry like that must have other knock-on effects.
Oh, absolutely. By changing the concentration of those key oxidants, MESH influences the atmosphere's overall oxidative capacity, its ability to cleanse itself.
Which could affect other important gases.
For sure. Things like methane, various halogen compounds. Their lifetimes and concentrations could also be subtly altered by the presence of MESH. It really highlights how interconnected everything is in the atmosphere.
So the bottom line here for climate science and modeling.
The clear message is that MESH needs to be included in climate models going forward. It's just too important to leave out, especially for the Southern Ocean.
For understanding past climate changes and predicting future ones.
Both. Getting the natural baseline right is crucial, especially as human-caused sulfur emissions from pollution continue to decrease. We need to understand these natural cycles better than ever.
It really underscores the complexity, doesn't it? The interplay between ocean life, chemistry, and global climate.
Definitely. And it's also, a reminder of how much we're still learning about the Earth system.
And while this is a natural process, it also throws the impact of human activity into sharper relief, doesn't it?
Yeah.
We need to understand both.
Absolutely. Understanding these natural regulators is vital, but it doesn't diminish the scale of anthropogenic climate change. If anything, it highlights the sensitivity of the system we're perturbing.
Okay, so let's try and wrap this up. The key takeaway seems to be the oceans, especially the Southern Ocean, are pumping out quite a bit of this gas, methanethiol, MISH.
A significant amount, yeah, around 19% globally, but more like 27% down south.
And this MISH does more than just add its own bit of cooling. It actually amplifies the whole process.
Right. It leads to way more sulfate aerosols, partly from its own breakdown, but also, really cleverly, by protecting DMS from being destroyed too quickly.
Giving DMS a longer life in the atmosphere.
Extending its lifetime, allowing it to build up more, especially in that critical Southern Ocean region.
And this enhanced aerosol cooling seems to directly address a long-standing problem in climate models that warm bias over the Southern Ocean.
It looks like a very strong candidate for explaining a good chunk of that bias, yes. It helps bridge that gap between models and reality.
It really is an aha moment, finding that this hard-to-measure gas plays such a surprisingly large role in regulating temperature down there. A whole new layer to the ocean-climate connection.
It certainly adds a fascinating new dimension, and it leaves you wondering, doesn't it?
Wondering what?
Well, it makes you think. Given that this one compound, MESH, was overlooked for so long but turns out to be so important, what else might be out there?
You mean other natural processes subtly influencing climate in ways we haven't fully grasped yet?
Exactly. What other connections or feedbacks are operating that we're only just beginning to uncover? And what does that mean for how we model the future climate as we keep digging deeper into these complex systems?
That's a really provocative thought to leave people with. Definitely something to chew on.
It shows how much more there is to learn about our planet.
Absolutely. Well, if you want to dig deeper yourself, definitely check out the original paper in Science Advances, and the UEA press release is a good summary too.
And maybe look into the Sea-law hypothesis, or the challenges of modeling clouds. It all connects.
Thanks for taking this fascinating deep dive with us today.